Now that we have the basic definitions for matrix transformations, we want to explore some of the common properties and operations. Our first property is arguably the most important. It's called linearity. A function, t, from Rn to Rm is said to be linear if, first of all, t maps the zero vector in Rm to the zero vector in Rm. 2, t applied to the vector sum v plus w is equal to t applied to v added to t applied to w. And 3, for any scalar a multiplied by t applied to v is equal to t applied to v scaled by a. The importance of this property is its ability to completely characterize matrix transformations. Our first proposition is the following. A function t from Rn to Rm is linear if and only if t is a matrix transformation. That is to say, t applied to v is equal to a times v for some m by n matrix A. The proof of this proposition is actually really instructive, so we're going to run through that. So first of all, we already know from previous work that a matrix transformation is in fact linear. So we'll first assume that T is a matrix transformation. So if T is defined by an m by n matrix A, then we already know from our previous work that T applied to 0, which by assumption is A times the 0 vector, is equal to 0. We also know from our work on distributivity that when you take T and apply it to the vector sum v plus w, that's the same thing as A times v plus w, is absolutely equal to AV plus AW, because we know matrix multiplication distributes across vector addition. And finally, we know that the order of scaling is interchangeable when we're doing matrix and vector multiplication. So this demonstrates that a function defined from Rn to Rm by an m by n matrix A is in fact a linear function. The new information here is that if T is linear, then T is defined by a matrix. So we remember that we defined the unit vectors E1, E2 through En that point in the n coordinate directions in Rn. So the key fact here is that these vectors allow us to express any vector in Rn as a linear combination. Next, we use the linearity of our function and the definition of matrix vector multiplication to construct the matrix for our linear function. So first, we use the second property that we can distribute the t across the sum. Next, we use the third property of linearity that we can pull the scalars out through the function evaluation. And finally, we think about these vectors t of E1, t of E2, down to t of En as the columns of a matrix. Since this is simply a linear combination in these new m-dimensional vectors, now we simply recognize that the column vector v1, v2 down to vn that we've written here is the original vector that we started with, v. So we can see if we choose A to be the matrix whose columns are t of E1, t of E2, down to t of En, then this arbitrary linear function that we've been given can be written as a matrix transformation. So now that we understand this in generality, let's do a couple of concrete examples. For our first example, we're going to define a function t from R3 to R2. Given an arbitrary vector whose coordinates are x, y, and z, we are going to map that to the two-dimensional vector x plus y, y plus z. First, we'll check that this function is actually linear, and then we will write down the matrix that defines it. The first property that we need to check is that t maps the zero vector in R3 to the zero vector in R2. This is pretty easy to see, for if we take the vector with 0 in all three of its coordinates, we add the x and the y coordinate, that's still 0. Add the y and the z coordinate, that's also 0. Next, we simply want to check that our function is in fact additive. We're going to take a vector x1, y1, z1, and another vector x2, y2, z2. We're going to first add those together, then apply t. When we apply t to this vector, we simply add the x-coordinate, which is x1 plus x2, to the y-coordinate, y1 plus y2. Then take the y-coordinate, y1 plus y2, and add it to the z-coordinate, z1 plus z2. Next, we can rearrange so that each of the pieces with the same subscript are grouped together. We can split this into two vectors which have been added together. Finally, we recognize that the first vector is t of x1, y1, z1, and the second vector is t of x2, y2, z2. So, in fact, we've shown that our function t is indeed additive. The third thing that we have to check is that our scalars can be pulled through the function evaluation. So if we choose a scalar a and a vector x, y, z, we can first scale our vector, then apply t. Next, we observe that we can factor an a out of each of the coordinates. We recognize that this is a scaled version of the vector x plus y, y plus z, and this vector is in fact just t applied to our original value vector x, y, z. There you have it. We've verified that each of the three properties necessary to be linear are indeed satisfied. So to construct the matrix which goes with this linear function, we just need to take the vectors e1, e2, and e3, apply t to each of those, and arrange those as the columns of a matrix. When we apply t to e1, we get 1, 0. When we apply t to e2, we get 1, 1. And then when we apply t to e3, we get 0, 1. So the matrix, which defines our transformation, has columns 1, 0, 1, 1, and 0, 1. In fact, you can actually check that if you apply the matrix A to an arbitrary vector whose coordinates are x, y, and z, you will in fact get t of that vector. And there you have it. That is how you verify that a function from Rn to Rm is actually linear, and how to find the matrix that defines a linear function. Next up, we want to talk about composition.